Okay, welcome to This Explainer. Today, we're diving straight into a radical, totally mind-bending proposition that challenges literally everything we thought we knew about the cosmos. For decades, right, the absolute bedrock of modern astrophysics has been this idea that our universe is expanding. We see galaxies moving away from us, we observe light stretching out across these vast cosmic distances, and we've built some incredibly intricate models relying on dark energy and dark matter just to make the math work out. But what if we've got it all backward? A fascinating scientific paper proposes an entirely different framework. What if the universe isn't expanding at all?
So let's start with a really profound thought experiment. What if the universe only appears to be expanding because you and, well, your measurement tools are actually shrinking? I know, it sounds straight out of a sci-fi movie, but the documents we're analyzing today actually lay out a highly structured mathematical and theoretical argument for exactly this scenario. Just imagine standing in a room and without you even realizing it, the ruler in your hand is getting smaller, bit by bit. And no, this isn't just a convenient excuse for why you aren't quite 6 feet tall. To you, standing there with your shrinking ruler, it would look exactly like the walls of the room are rushing away.
And that brings us to the decreasing universe theory, or DUT for short. This is a unified model proposing that extremely slow, continuous gravitational contraction creates the cosmic illusions of our era. The core hypothesis here is that a gravitational field doesn't just curve space, it actually causes a continuous contraction of space and everything inside it. We're talking physical matter, atomic standards, and yep, the very instruments we use to measure the universe. Now, because we are inside this gravitational field, we obviously don't feel ourselves shrinking. The effect is cumulative over vast cosmological timescales, mimicking what we've traditionally been calling the accelerated expansion of the universe. Let's move into our next section. The illusion of expansion, rethinking our shrinking rulers. To really grasp this paradigm shift, we've got to look at the core illusion. In the standard model, the fabric of the universe is stretching out. But under DUT, if your ruler gradually shrinks, the room you're measuring will falsely appear to be expanding. According to the source material, this contraction is completely imperceptible on a human scale. You wouldn't notice it going about your daily life because your biological cells, your watch, your measuring tape, they're all contracting at the exact same proportional rate. The discrepancy only really reveals itself when we look out across the universe at light that has traveled for millions or billions of years, entirely free from our local gravitational contraction.
Next up, the shrinking hypothesis and the math behind the contraction.
Now, the researchers don't just rely on some fun conceptual thought experiment, they actually back it up with hard math. This equation elegantly illustrates how apparent distance grows exponentially as time passes, driven by the Hubble constant, without space itself actually stretching. Let's break it down simply. D represents the apparent distance measured by us on Earth. D0 is the actual co-moving distance, and delta T is the time it took the light to reach us. So the Hubble constant, which we've traditionally thought of as the rate of cosmic expansion, is actually reinterpreted here as the rate of our own gravitational contraction. Crazy, right? As our local standards shrink over time, the apparent distance to extragalactic objects just multiplies exponentially.
Moving on to redshift and time, where we'll be reinterpreting cosmic light.
So redshift, that observation where light from distant galaxies shifts towards the red end of the spectrum, is usually taught as the literal stretching of space pulling light waves apart. But if we walk through these steps, we can see it reinterpreted as an artifact of our own contracted measuring stick. Step 1. A photon leaves a distant galaxy and travels through the near vacuum of space, where gravity is practically zero, meaning the photon doesn't contract at all. Step 2. Here on Earth, subjected to our local gravitational fields, we've been continuously shrinking over those billions of years. And finally, Step 3. When that ancient, uncontracted photon finally arrives, we measure it using our modern, deeply contracted instruments. So naturally, the photon's wavelength appears massive to us. It shifted red not because the universe expanded, but simply because we got smaller.
Which brings us to a really provocative question. The end of dark matter? Let's take a new spin on galactic rotation.
For decades, astronomers have observed galaxies spinning so incredibly fast that they really should just fly apart. This prompted the invention of invisible dark matter to hold them together with extra gravity. By juxtaposing the standard model with DUT, we can see exactly how this alternative theory attempts to unify some really complex phenomena under one gravitational roof. In the standard model, we rely on mysterious, completely unobserved elements, dark energy to push the universe apart, and dark matter to hold galaxies together. But the decreasing universe theory comes in and claims we don't actually need these invisible placeholders at all. Instead, it suggests that stars on the outer edges of a galaxy experience far less intense gravity than stars near the core. Because of that, the outer stars contract slower than the inner stars. This differential in contraction alters the light they emit, which we basically misinterpret as anomalously high orbital speeds.
And here's where it gets really elegant. Instead of relying on invisible dark matter, DUT derives the famous Tully-Fisher relation completely natively. If you aren't familiar, the Tully-Fisher relation is an observed rule that a spiral galaxy's mass is proportional to its rotation velocity to the fourth power. The source material mathematically proves that by simply applying the laws of gravitational contraction to the galactic disk, you arrive exactly at this famous relation. It beautifully deduces empirical astrodynamics from just one core assumption: no dark matter required.
All right, let's look at tests and evidence. Here is the observational data supporting DUT.
Because a theory is really only as good as its observable predictions, right? So let's examine the empirical data presented in the paper. The logic goes, if gravity causes contraction and contraction causes redshift, then objects with more gravity or objects that are older should exhibit very specific redshift patterns that standard cosmology wouldn't normally expect. Well, out of 50 galaxy pairs tested, a staggering 94% demonstrated that the more massive galaxy had a lower redshift, which aligns perfectly with Dutt's prediction. The paper details that if you look at two galaxies sitting at the exact same distance from Earth, but one is far more massive than the other, the massive one has a stronger gravitational field. Under Dutt, that stronger gravity causes greater contraction of its local light standards, resulting in a smaller emitted wavelength, and that translates directly to a lower measured redshift. Literally 47 out of the 50 pairs analyzed in the documents perfectly followed this exact rule.
And when we organize galaxies by age, another striking pattern emerges. Older, elliptical galaxies consistently exhibit lower average redshifts than younger spiral ones, suggesting they've just had way more time to gravitationally contract. By comparing galaxy populations inside the Virgo, Coma, and Centaurus clusters, researchers treated elliptical galaxies as the older population and spirals as the younger ones. And the results? In every single cluster analyzed, the older galaxies exhibited a noticeably lower redshift. The theory explains this beautifully. Older galaxies have simply been around longer, so they've had more time to gravitationally contract. More contraction means shorter wavelengths emitted, which means less redshift. It fits together like a giant puzzle.
Let's move to our final section, the scientific verdict, a reality check and limitations.
Now, while this is all mathematically very elegant, we've got to impartially ground ourselves in scientific reality here. Science thrives on skepticism, and as detailed in the documents, these self-acknowledged limitations prove that while DUT is a totally fascinating unifying program, it needs a lot more work. It requires much larger, independent astronomical datasets before it can truly challenge the standard model. For instance, the researchers totally acknowledge that looking at just 50 galaxy pairs is a relatively small sample size. Furthermore, using stellar mass as a proxy for a galaxy's total mass can definitely introduce some errors. They also admit that the effects of galaxies moving independently within their clusters, what astronomers call peculiar velocities, well, that makes the data pretty noisy. For this to be accepted by the broader scientific community, the theory requires rigorous, independent testing across vast catalogs of galaxies, directly pitting its predictions quantitatively against the standard cosmological model.
So, as we wrap up this explainer, I want to leave you with a question to ponder about the incredibly fluid and ever-evolving nature of astrophysical science. Is the decreasing universe theory the next huge paradigm shift, or just a beautiful mathematical illusion? Whether DUT eventually rewrites the textbooks or just serves as a brilliant exercise in alternative physics, it forces us to step back and completely reevaluate our deepest assumptions. It reminds us that sometimes what looks like the universe running away from us might just be a trick of the light, viewed through a steadily shrinking lens. Keep questioning, keep looking up, and stay curious.